Next, we're going to talk about the area under a curve. And this is one of the most important ideas in calculus. It is to integration as the tangent line problem is to finding the derivative. So what we have here is a curve, and it says let f of x be non-negative. So you can see that it's above the x-axis here on an interval from a to b. So let's just draw that interval. We'll just say this will be a, and we'll just call b somewhere over here. Okay, and what we want to do is find the area of the region lying beneath the curve y equals f of x, so below this curve, and above the x-axis, so above this line right here, from x equals a to x equals b, so in between these two lines right here. So we're going to be looking for this area right in here. Okay, so that's what we're going to be doing. Now, a way of approximating this area is to divide the region into a series of rectangles that either fit just inside the region or just outside the region. Then add the areas of the rectangles up to approximate the area of the region. And by increasing the number of rectangles, you can obtain closer and closer approximations of the area of the region. So let's go ahead and see what we're talking about here. So let's go ahead and draw our region, okay, from A to B. And we want to divide the region into n equal subintervals having the width of delta x. And so we can just use these hash marks right here to help us divide this into our subintervals. And if we're talking about a left-hand sum, okay, we're going to be dealing with left endpoints. Okay. And so we're going to use all of these endpoints here on the left of the intervals to create rectangles. So you can see we have a rectangle here, 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 and here. So what we're talking about is if I can find the area of all of these rectangles and then add them up, that's going to be an approximation that's slightly under the area that we're looking for. And you can see here, like we got this little bit of extra area that we're not accounting for right there. Now it does say as we increase the number of intervals, this amount of wasted area or missed area is going to decrease. So let's talk about how we would find the area of these rectangles. Well, what we do is we let this first x value be x sub 0. Then we would let the next one be x sub 1, and then x sub 2, okay, so on and so forth, all the way to x sub n minus 1, and then this would be x sub n. Okay, so next we have to think about finding the area of just one of these rectangles. And we know the area of a rectangle is going to be length times width, right? So the length in our case is actually going to be the height of the rectangle. Okay, and we know that this height is going to correspond to the y value right here, which is going to be f of x sub 0. Okay, and that's going to be the height of this first rectangle. Now, what is the width of the rectangle? Okay, well, the width is actually going to be what we call delta x. And it's going to be the difference in these two x values, x sub 0 and x sub 1. Okay, so from this information now, we can go ahead and come up with an approximation for our left-hand sum. And I'm going to abbreviate this as LHS for left-hand sum. So So our first rectangle here is going to be f of x sub 0 times delta x. Now my second rectangle is going to have this as its height, and that's f of x sub 1 times the width of delta x again. Okay, and this process would continue for all of the rectangles up until this one. This would be our final rectangle right here, and that's going to be f of x sub n minus 1. Okay, because it's 1 before the last term there. And, of course, it's times delta x. Now what we're going to be able to do here is you can see that this is going to be a sum. So we're actually going to write this now using summation notation. Okay, and it's always going to be I equals 1 to n of f of x sub I minus 1 times delta x. So if you were to find this left-hand sum, you would find the sum of all these rectangles, and it would be an approximation for the area under this curve. Now you'll notice that this all used left endpoints. And you can see them all here. Now, when we use the left endpoints, we want to know how can we figure out what x sub I minus 1 actually is. So here, if you need to find left endpoints, and you need to find x sub I minus 1, that's always going to equal a, or the starting value of our interval, plus I minus 1 times delta x. Okay, now you can always find delta x using this formula right here, which is going to be b minus a over n, or the end of your interval minus the beginning, and divided by how many subintervals or how many rectangles we want to have in there. So this formula right here is going to give you what x sub I minus 1 is to use in our function for our sum. Now, if we want to talk about a right-hand sum is going to use right endpoints. So let's go ahead and get our values from a to b, and then we'll divide it into n subintervals. So notice there are more here. I'm just using this to show how it is. Now, if we're going to do a right-hand sum, that means we want to use the right endpoints right here. So start at the right of your interval and work your way down or to the left. And now if we want to create rectangles, they're going to have these heights. And you can see the extension right there. Okay, so these are all right endpoints. Okay, now if we're looking at this problem, our x values are still the same. So x sub 0, x sub 1, x sub 2, so on and so forth. This would be x sub n minus 1, and here would be x sub n. Now, if we're trying to find our rectangle, the area is going to be this height now times the width. And this height is going to correspond to f of x sub 1, okay? Or f of this x value right here. And it turns out that our delta x is still the width of the rectangle, and is determined by this formula right up here. Now, if we're going to write this as a sum, notice we're going to start here, but we're going to end up going all the way now until x sub n. So for our right-hand sum, or RHS, we're going to start with f of x sub 1 delta x, and then go to f of x sub 2 delta x, so on and so forth, all the way up to f of x sub n delta x. So your right-hand sum is still going to be the sum from I equals 1 to n. So it doesn't change. We're going to start at 1 to n intervals, but now we're just going to have f of x sub I times delta x. So hopefully you can see that the delta x's don't change. That's why we can factor that out there. Now, if we're looking for the right endpoints, and we need those x values of the right endpoints, which are x sub I, now it's just going to be a, or our starting interval, I times delta x. So before it was I minus 1, now it's just going to be I. Now this right-hand sum is going to give you the sum of all of these rectangles formed by the right endpoints. And now this one's going to be an approximation, but it's actually going to be an overestimate, okay, because we have this little bit of extra areas right in here. So if we look at the left endpoints in this case, this one's going to be an underestimate. And if it's an underestimate, we call it a lower sum. And if it's going to be an overestimate, as in this case, then we call it an upper sum. Now it turns out left-hand sums are not always lower sums, and right-hand sums are not always upper sums. What you have to do is look and see, are the rectangles below or circumscribed, meaning inside, or are they circumscribed, meaning outside? And so you have to determine lower sum and upper sum based on how the rectangles look. Okay, so that's how to find left-hand sums and right-hand sums. So since f is continuous, f has a minimum and a maximum value on each of these subintervals. And for our purposes, these will always correspond to a left endpoint or a right endpoint on each of the subintervals. And so for a lower sum, we are going to use a lowercase s of n, so it's the sum of all the rectangles. And we get this notation where we have a lowercase m right here. And then the upper sum is going to be your circumscribed rectangles, and we get a capital S of n, and notice we have a capital M sub I right here. So the lower sum again is going to be the smaller approximation, and the upper sum is the upper approximation. But the big thing to realize is that the actual area is going to be somewhere between the upper and the lower sum. So for now, whenever it says approximate, I want you to go ahead and find the lower sum and the upper sum, and the area has to be somewhere in between that. So let's try an example now. It says use upper and lower sums to approximate the area of the region under the curve. So we have f of x equals x squared plus 1 drawn here, and we want to go between a equals 0 to b equals 3. So a equals 0 is right here, and then b equals 3 is right here. So you can see this is the area we're looking for, and in this case it's telling us delta x equals 1, meaning we're going to put a new subinterval every 1 apart. And you can see that gives me 3 equal subintervals. If we want this to be a lower sum, that means we need inscribed rectangles, meaning we need to draw rectangles underneath the curve here. Now what type of endpoints are these? Okay, well, it starts all the way on the left, so these are actually going to be our left endpoints. And in this case, when we have left endpoints, we're going to be looking for the left-hand sum. So let's just go ahead and work this out numerically. So this right here, this height would correspond to f of 0, right? Because this x value is 0. So there's our height times our width of delta x. So I'm just going to put delta x here. And then plus our second rectangle, which will have a height of f of 1. And it will also be times delta x, or the width. And then we have our third rectangle right here, which is going to be f of 2 times delta x. Okay, so let's go ahead and just substitute in our numbers here to come up with our left-hand sum. So f of 0 means we're going to plug 0 into our function here. So we have 0 squared plus 1 times delta x, which in this case is just 1. And then times f of 1, so we're going to plug 1 into our function. 1 squared plus 1 times delta x, which is 1. And then f of 2 is going to be 2 squared plus 1 times delta x, which is just 1. And when we add all this up, this equals 1, this here is going to equal 2, and this is going to equal 5, and so our sum is 8. And this right here is our lower sum. Okay, let's go ahead and find our upper sum now. So we're still on that same interval. So I always like to draw my subintervals here just to start with. And now we want an upper sum. So the uppers mean we're going to have a circumscribed rectangle, meaning it's going to be above. So we need to draw the rectangles that are above. It includes this one. So here's our 3 rectangles, and let's go ahead and look at this in terms of being a right-hand sum with the right endpoints. Okay, so you can see that these ended up being right endpoints here. And so our right-hand sum is going to be f of, well, now we're going to use the right endpoint. So f of 1 times delta x plus f of 2 times delta x plus, right here, f of 3 times delta x. And so let's go ahead and substitute everything in here. So we get 1 squared plus 1 times 1 plus 2 squared plus 1 times 1 plus 3 squared plus 1 times 1. And so this was 2, this was 5, and this is going to be, let's see, 10 right here. And so this sum is going to be 17. And this is our upper sum. So it says approximate the area. So remember, when we said an approximation for the area, it's going to fall between the upper and the lower sums. So it's going to be greater than or equal to 8 and less than or equal to 17. And so here is our approximation. Now notice in this example we didn't use any of our summation formulas, and I chose not to because this was a fairly simple function, and we could find the sum very easily without using summation notation. We could just look at the rectangles. Let's try our next example. It says use upper and lower sums to approximate the area under the curve. So now we have our function f of x equals 12 over x, and we want to go on the interval 1 to 4. So let's go ahead and draw that. Here's 1 and here's 4. And now we say that n equals 3, meaning we're going to have 3 subintervals. So the first thing I need to find here is delta x. Okay, and that's going to be b minus a, or 4 minus 1, over n, which is 3. So in this case we get 3 over 3, which is just 1. So here delta x equals 1, and that's going to allow me to draw in the rest of my subintervals. And let's go ahead and start by finding the lower sum. So in this case, the lower sum has to be the rectangles underneath. So we're going to draw them here. Okay, and then what type of endpoints are these? Well, they're on the right side of the rectangles, so these are right endpoints. Okay. Now in this example, we do want to use our summation notation for right-hand sum. So you'll recall that when we're finding a right-hand sum, we have the sum of I equals 1 to n of f of x sub I delta x. Okay, so notice in this case, even though it's a lower sum, it is a right-hand sum. So that's going to be very important. And so looking at this, we know n equals 3. Let's go ahead and find x sub I. That's our next goal. So x sub I is going to equal a plus I times delta x. So in this case, a is the beginning of our interval, which here is just 1. And then I times delta x is just 1, so it's 1 plus I. Okay, so x sub I equals 1 plus I. So let's go ahead and substitute in everything we know here into this sum. We know we go I equals 1, n equals 3, so it's the number of subintervals. And this is going to be f of 1 plus I. And then delta x is going to be times 1. All right, and we can make this even a little more clear by substituting I plus 1, or 1 plus I, into our function f. So our function is 12 over x, so this is really going to be 12 over 1 plus I. And then the times 1 didn't matter, so this is the sum that we need to find. And so let's go ahead and just solve it. It's only 1 to 3. So we do 12 over 1 plus 1 plus 12 over 1 plus 2 plus 12 over 1 plus 3. And so this gives me 12 over 2, which is 6. This gives me 12 over 3, which is 4. And then 12 over 4, 3. And so my total answer here is 13. Okay, and remember that is my lower sum here. Okay, so let's go ahead and find our upper sum now. So again, I always like to draw in, we'll use the same intervals as before. And now we want an upper sum, so we need circumscribed rectangles. So all my rectangles have to fall above the curve. And in this case, which endpoints do we have here? Well, these are going to be left endpoints, meaning we're going to be finding our left-hand sum. Okay, and so our sum here goes I equals 1 to n, and this is going to be f of x sub I minus 1 delta x. Okay, so let's go ahead and find, for our left endpoint, x sub I minus 1. So it's going to be a plus I minus 1 delta x. And a, we said, was 1, because that's the start of our interval. And then I minus 1 times 1. And all of this is just going to equal I. Okay, so x sub I minus 1 is just going to be I. So let's rewrite this sum now. It's going to go from I equals 1 to 3 times f of I, and then delta x, which is 1. And then let's substitute I into our function. So this is going to be the sum of I equals 1 to 3 of 12 over let's see, I times 1, and so we can just leave it there. Alright, and that sum's going to be easy enough to calculate by hand, so we'll just do it that way. 12 over 1 plus 12 over 2 plus 12 over 3, and so we get 12 plus 6 plus 4, and that is 22. So an approximation for the area is going to be between our lower and our upper sum. And notice the lower one's going to be smaller, the upper one's going to be bigger. So it's going to be greater than or equal to 13, less than or equal to 22. Alright, let's go ahead and try our next example. Alright, and I want you to try example 1C on your own. At least try to get it into your summation notation, and then for this one you might want to use your calculator to actually find the sums, since they're going to be a little bit more difficult. And then go ahead and write your area as an approximation. So go ahead and pause the video, come on back when you're done to check your work. Alright, welcome back. Go ahead and check your work here on finding your lower sum and your upper sum, and see if you can figure out if you got off track anywhere or if you got stuck. Try to figure this out. If you have questions, please bring them to class. So this was how to find an approximation of an area under the curve using lower and upper sums and right hand and left hand sums as well. Alright, thanks for watching, and we'll see you in class.